right, let's start on time. Okay, so in this lecture, so we're going to talk about, actually, we are going to wrap up our discussion on Verilog first. Then we'll start a brand new topic called finite state machines, or FSM. Okay. So as usual, a few announcements. Homework 2, I think, right? That's due tomorrow. Against midnight, right? So that's a deadline. And also make sure that you guys pay attention to the deadline for Lab 2A. It's actually due on Monday, the next week, right? On the 8th, not on Wednesday, because we have this wellness days, right, coming up. You guys are gonna have this a mini break, right, which is well deserved. That's why we're gonna make sure that you guys check out right before Monday. So in case you have already finished the lab, make sure that you don't have to wait until the lab sessions, right? We have 2 lab sessions on Monday, but you can actually go to any of the TA office hours to check out your lab. Okay. And of course, there's no lecture on Tuesday, and also there's no lab on Wednesday. Okay. And also, we'll give you guys more details about Protein 1. But here are some more details, right? So it's going to be open book, open notes, right? Again, 75 minutes. But you are expected to sign into Zoom at least 5 minutes earlier, because we are gonna make some announcements, right? Let you know, what are the right, so the specific things that you need to do, and also make sure that you have your camera on. Okay, Mitch was asking, so the camera face or paper or both, right? So hopefully you get to see both of you and right, the exam that you're working on. Okay. And unless we want to see you, Mitchell. Also, we will post more instructions next week. Okay. But make sure that you have a webcam, or at least you test your camera right on your laptop. Okay. So let's talk a little bit more about Verilog, right? Last time I gave you guys a very quick intro, right? We just quickly went over some of the concepts, right? Then we focus most of our time on the so-called procedural assignments, right, in Verilog. We actually talk about both 2 kind of assignments. So one more for the computational logic, right? So that's called continuous assignment, right? So there we basically have something called assign, right? So this is a keyword, and also we are introducing this important, right? This is a keyword called always, right? So this always block is very important for us to create meaningful designs. So including both computational and sequential design in Verilog. I'm going to talk a little bit more about blocking and non-blocking assignment later on. Okay. But just want to make sure that when you guys write these Verilog statements, right, whether it's sort of instance statement, right, you can instantiate new modules, right, you can build things hierarchically, or you can use this continuous assignment, or you can also write these always blocks, right? So the order, right, you can write them in any orders that you want, as long as they are readable. But really, you're actually modeling a concurrent hour, right? So this is really something that you guys need to pay attention to. Yeah, so unfortunately, there's some noise, there's some background noise, right? So there's a construction near my place these days. Sorry about that. Okay, hopefully it's not too bad. Okay, you can still hear me clearly, right? Cool. All right. Okay, so this is the quiz that you guys did, right, last time, right? So three code snippets, right? We'll start with the third one, right? I'm asking you guys to figure out whether we are doing sequential logic or combinational logic, right? So that's really the question. So let's focus on the rightmost one. Is this one combinational or sequential? Combinational, right? There's even, right? So clock is not even involved, right? And basically every time A and B changes, right? So input changes, output responds right away, right? This is not sequential. Okay. Next one, what is that? So what is Z? So this is something about Verilog, right? So we're going to talk about Like more, right? Reg can become either wire. So in this case, this is a wire, right? This is a wire, right? This is combinational. This one becomes what? It's the, oh, look at the sensitivity of this, right? So there we have pause edge, right? So this is sequential, right? This is basically a flip-flop, right? Z. And Z changes at the clock tick or at the rising edge, right? Right after the rising edge. Okay, so if you guys got this two right, then you will get full credit, okay, for the quiz. Okay, so these two are important, and actually intentionally, make this quiz a little bit tricky in the sense that you look at the leftmost one. Okay, it's actually not a good design. The left one is sort of buggy. Okay, so it's actually not really clear, right? So is this sequential or combinational, right? Although clock is on the sensitivity list, but clock is not really used in the always block, right? Is this latch? It's not, right? First, the sensitivity on sensitivity list, right? So we are not using pause edge. This is definitely not flip-flop. Right? Okay, so to help you guys reason about this a bit more, let's go back to this. Let me switch my screen. Let's go to this EDA playground, this website that I showed you guys last time. Okay, let's just play with this code. Okay. All right, so here's the code, right? And this is the quiz block, right? That we created, 2 inputs, 1 output, right? In the always block, right? So again, just to remind you guys, right? If you have something on the left-hand side, right, being assigned or written, so we need reg. Okay, so we need reg. So for all the signal being written in the always block, right? And you cannot have the same signal written in more than one always blocks. That's going to cause conflict, right? Again, everything's concurrent. And so this is not really doing something interesting, right? So because clock is, although clock's on the list, but we don't assign to Z when clock is low or high, right? So this is not a level sensitive device. Does it make sense? Right. So this is not a latch, right? So maybe you can fix it. Right? Let's say if clock, right? Fix it. This seems more like a latch, right? Okay. Let's just run the waveform. Okay, so see here, right, clock is indeed right. So this is my test bench, right? So I'm changing. So A, right? So first 0 0 and then 1 1, right? So this is the end, right? So for Z, right? I did not reset Z, so Z is right. This is don't care. Okay, so this is red, right? This bit don't care. But see here, somehow, although right, clock is high over here, right? See this waveform, clock is high, and A and B they are changing. Somehow Z is still stuck at 0. Right? This is also not a latch for some reason. Agree? So right now, this is not behaving like a latch, right? So what's going on? How do you fix this code? So there are some questions. I'm going to respond to the question. I cannot see the chat window right now. How do you fix this? So one thing is, maybe I should go to the chat window somehow. But I have to stop sharing on the screen. Okay, why is it not a latch without the if statement? Because almost asking, right? Because you can switch at clock 0 or clock 1, so whenever clock change value, right? So it's indeed we are sensitive to the clock, right? The change of the clock. But think about the definition of latch, right? If clock is 0, right, then we are not supposed to take new values, right? Only if clock is high, right? Only if the enable is high, you're supposed to take value. That's the definition of the latch, right? It's level sensitive. Make sense, Amma? Okay. So how do you fix this? How do you make it a latch? Any suggestions? Let's think I can see the chat window now. So Lauren saying post edge, right? So if you put post edge there, right? We can do the edge thing, right? So you're talking about this one, right? Put it here. So that means we make Z sort of like a flip flop, right? It's becoming edge sensitive. Okay, so this is something that I want you guys to notice, right? So this is why I created this quiz, right? The buggy one, right? Intentionally, so that later on, you may hopefully you can avoid this mistake, right? So really, this always block is not responding to A and B, right? So that's the purpose of the sensitivity list. Okay, so if we make this change, right? So before, regardless whether A or B changes or not, right? This Z is going to stay at the same value. Make sense? Right, so you make this change here. Now we have a nice latch, right? So when clock is high, okay, so Z is responding according to the change of A and B, right? It's going high and then low. All right, so pay attention to the sensitivity list. Right? In many cases, right, this is just fine. This is a wildcard. Like just putting in a star means that we are going to be sensitive to anything, all signals on the left-hand side, including clock, A and B. And this is the easiest way, okay, in many cases. All right, so if you run it again, right, again, this is a good latch. Okay, any questions? I need to go back to the other screen. Okay. Right, so there are some more questions in the sensitivity list. Do all need to change or just one? Yeah. So I think we discussed this last time a bit, right? So if one of the thing, right, if one of the signals on the list changes, then the always block is supposed to be triggered. That's a simulation behavior. Okay. All right, but if you think about the previous case, right? So like in this case, if A and B, they are not on the list, right? Even though clock stays high, right? Z is not going to take in new value because, right? So it does not, right? This always law does not respond to A or B. Okay, it's not sensitive to A or B. Okay, so this is the quiz, right? Like I said, right? These two are more important, right? Okay, if you got this right, you pretty much got the important thing about always block. Okay. Last time we also talked about this somewhat confusing aspect, right? Blocking and non-blocking assignments, right? This is we have two kind of right operators. One is this equal sign, is the blocking, right, and this arrow or less than equal is non-blocking. Last time we talked about simulation behavior. What do I mean by simulation behavior? It's really the algorithm that the CAD tool, right, like model sim, uses to generate a waveform, right? When model sim looks at its code, model sim, will follow this procedure, right, to generate a waveform. So basically, what model sim will just assume that for blocking assignment, the assignment is immediate. Okay, and for non-blocking assignment, the assignment is delayed, so it happens at the end of the always block. Right? So I told you one trick, right, to read these things, right? So one way to read this is for blocking assignment, you can just follow the order, right? You just from top to down, right, top down. And for non-blocking assignment, you read it this way. Okay, you reverse the order. So this way, you will get the simulation behavior right. Right. Again, so this is just simulation behavior, right? So what does that mean, right? So why do we need these kind of assignments, right? So why are they necessary? It's really about, because this is a model, right? This Verilog is basically a model of the actual hardware. So we actually want to use it to model something meaningful in the circuit, right? Again, these are the, right? So after the simulation, right? So if you simulate it right, so these are the signals, right? The values of the next, right? States that we are supposed to see. Okay, but the more important thing that I really want you guys to understand is, right? So these are just the simulation behavior, but the reason that we are having this is because, since we are doing it always block, right? In this case, coming back here, right? So we have a bunch of flip-flops, right? So later on in this class, we'll be mostly dealing with the flip-flops, right? So I'm going to talk about the reason pretty soon. So in one of the later lectures. So we actually don't like latches. We like flip-flop much better. Because they are edge sensitive. Over here, right, we have always block, right? So non-blocking, blocking assignment, they only differ when we have multiple statements, right? When we are assigning to multiple things in the always block. When we have multiple assignments, that means we have multiple flip-flops, right? And in many cases, right, when we build circuits, these flip-flops, like this, right? So this is a flip-flop, right? This is a flip-flop. They often interact, right? In an interesting way, right? Because we want to model more complex behavior, right? So in some cases, right, we may want to, for example, when we interact, right, we want to take the input side from certain flip-flop and then process it, right? And in some other cases, we want to take the output side, which is the delayed version, right? The one cycle delayed version of the flip-flop, right? So that's actually where, we just make use of these different kind of assignment operators. So do you guys remember, like for this one, for this version, okay, over here we are using the input side of y, right? This is basically the same thing with the input side, right? This is d side y, and then we connect it, we invert it, and then connect it to z. So what kind of assignment do we use here? Blocking or non-blocking? Anyone remembers? Blocking, very good. Right? We use blocking assignment. Okay, blocking is sort of combinational. Think of this way, right? Because the assignment is immediate, right? So that's sort of combinational. So this is intuition. And if you look at the second version, right, like the different circuit, right? So we are using the output side, right? We're connecting the output side of y. So it's really the delay version of y, right? So that's where we are using non-blocking assignment. So that's why, when we simulate it, right? So we also assign at the end of the always block, right? So basically we take the delayed version, the delayed value. Okay. Hope this makes sense, right? I'll give you guys a bit more so exercise, right, in homework as well. So just want to make sure that this makes sense, right? Again, there's certain behavior that we during simulation and after synthesis. Okay, this is what we got, right? After synthesis, also this is what we want. So this is the other way around, right? So you should have some circuit in mind, right? You want to build certain circuit, and then you write it in certain way in Verilog. That's usually what happened. Okay, so like I said, right, last time, very quickly, right, so for blocking assignment, you take the input side, right, with the D side, and for non-blocking assignment, you take the Q side, output side. All right, any questions about this? If not, let me talk a little more about Verilog, because last time I think there's also a question about what's the difference between wire and reg, right? So these two are also somewhat similar, right? So how do we distinguish them? Actually, for wire, that really means a wire, right? So basically, it's just something that we connect, we use for connection. Eventually, this wire indeed will be inferred or synthesized into actual wire in the circuit. Okay, and this is really stateless, right? So this is wire. And for wire, right, when we do assign, right, continuous assignment, we can only assign to wire, okay, for conditional logic. So this is one important thing. And we cannot use wire, right? We cannot use wire signal in always block. When we assign to a signal in always block, we always need reg. But one confusing thing about reg, right? There's actually one confusing thing about Verilog, is this reg can be synthesized into wire, latch, or flip-flop. We already talked about this, right? But when we have always lock and we assign things, we always need the reg. Okay, so these are the differences, right? But a reg can turn into wire in some cases. And let's see an example. Okay. So I think some of you are already running into this issue, right? As part of lab 2, right? You might have seen this warning from Quartus, right? Saying that there's this infer latch, right? We also want you guys to avoid creating infer latch. What exactly does that mean? So usually with always block, right? So usually, in many cases, we'll just ask you to write always block, right? But when you try to use always block to model combination logic, you want to be really careful with how you assign to things, right? How you assign to output signal. If you do not, so especially when you have if then else, when you have conditional, like control flow. So in this case, for example, you actually want to create sort of a mux, right? You have a D, right? Input D, and then you have select signal. But if you write an incomplete if then else statement like this, so the cato is going to infer a latch. Why is that? Anyone knows? What's the intuition here? Why is that? We already saw a latch example, right? In this EDA playground on this website, right? So why is this one a latch? If you have the answer, right, just chime in. Feel free to unmute and chime in. Because this is going to be important, very useful for your lab, okay? Understanding this part. Very good, right? Lauren saying that we do not set a new value, then the last one is used, right? Mamoon is saying the same thing, right? Right. Same. Kate is also saying this. Right? So basically over here, so this out is going to be inferred as a latch, which is sensitive to select, right? The signal. It's a level of sensitive device, right? It's sensitive to when SEL or select is high, right? We assign to out. But otherwise, what do we do? So because we did not really specify the complete, right? The condition, right? So when select is over here, we are saying when select is 1, out is going to be updated, right? With D. But when select is 0, we did not specify that. That means out is going to retain the previous value. That's where we have a stateful element, right? So that's why we have a sequential logic here. And this is a latch. Okay, so this is an infer latch. So really, in many cases, what you mean to design is something like this, right? So you actually want to do something like this, right? So you want to do a combination logic, right? When select is 0, so you actually want to take the inverse, right? The inverted value of D. And make sure you put it there. And make sure that under any given input combinations, right? So if you actually intend to design combination logic, the output signal is assigned. So what is this? So this is really a mux, right? Over here we have a mux. Right? This is like a mux, basically D naught, right? And it's assigned to out, and we use select here. Right. So when later on when you guys see infer latch, don't panic, right? So first think about, do you want combination logic or not? If you want combination logic, make sure they check all the conditions. Otherwise, if you want D flip-flop or register, check the sensitivity list. Right? Check whether you are responding to, you're sensitive to the clock or the edge of the clock or clock edge. Okay, so these are the 2 things you want to check. All right, any questions about infer latch?